In the last video, we talked about events which were independent or not independent. And we talked about that in terms of, does knowing that one thing occur not change the probability of the other thing occurring? But if two events are not independent of each other, if we know one has occurred, that changes the probability of the other occurring. And working out those changes, we need a tool called conditional probability. So this is some notation we'll use. The probability that A happens, given that B has already happened, we're going to use this vertical line. A given B. And that's how we say it, A given B. And that means, what's the probability of A happening if we know B has already happened? And the formula we use to work that out is the probability of both A and B happening, A intersection B, divided by the probability of B happening. Why does that formula work? Well, if you think about our equally likely scenario, probability of A happening is the size of all the outcomes that correspond to the event A divided by the size of the universal set, all the possible outcomes, the sample space. Think of that in terms of a Venn diagram. So we've got the probability of A is the size of the red area A divided by the size of both the red and the blue area, everything that could possibly occur. Now, if we know B has already happened, a lot of this sample space can't happen anymore. So if we know B has already happened, we are restricted to B. We are restricted to within that circle of B. None of the things outside of that circle can happen anymore. So now if we want to know what's the probability of A happening, and we know B has already happened, it's that red area, which is the size of A intersection B, divided by the red and the blue area, which is the size of the event B. And so that's analogous to probabilities. Probability of A, if we know B has already occurred, if we are restricting our sample size to just B, is the probability of the intersection of A and B divided by the probability of B. Let's think of an example just to get a feel for what this means. So a person is chosen randomly from the population of the UK. Let A be the event that that person is a basketball player. And let B be the event that that person is taller than 6 foot. What's greater? Which probability is bigger? The probability of A given B or the probability of B given A? So let's interpret that. What is bigger? The probability that you are a basketball player if I know you are taller than 6 foot, or the probability that you are taller than 6 foot if I know that you're a basketball player? So just the way we would answer this with just feeling would be, well, most basketball players are tall, and so most of the basketball players are bigger than 6 foot, so that must be bigger than the other thing, which is asking, out of all the people who are 6 foot, how many of those are basketball players? Well, you can be tall and not be a basketball player, that's fine, but there's plenty of people out there who are tall and are not basketball players, but there's not many short basketball players. So that's the feeling we get for it, but we can actually show this mathematically as well. Okay, so we want to ask the question, what's bigger, the probability of A given B or the probability of B given A? Well, we know that the probability of A given B from our formula for conditional probability is the probability of A intersection B over the probability of B. And the same for the probability of B given A, that is the probability of B intersection A over the probability of A. Now notice the tops of these fractions are both the same. Intersection of A and B is the intersection of B and A. So we're only looking at the bottoms now. What's bigger, the probability that you are taller than 6 foot tall, or the probability that you're a basketball player? Well, there's a lot more people who are 6 foot tall than there are basketball players. And so the probability of B is much bigger than the probability of A. So we are dividing by a bigger thing. So this whole thing is smaller than this thing, which corresponds with our intuition. Let's look at another example now where we're going to start calculating conditional probabilities. So this example, in Mexico, 32% of people are Garth Brooks fans. Great people. In Mexico, 8% of people both dislike the government and are Garth Brooks fans. What is the probability of meeting someone who dislikes the government at a Garth Brooks concert? So at the Garth Brooks concert, you're going to assume everyone's a Garth Brooks fan. So we're asking, what is the probability of meeting someone who dislikes the government out of the Garth Brooks fans? Okay, let F be the event that you're a Garth Brooks fan. Let D be the event that you dislike the government. What do we know? We know that the probability of being a Garth Brooks fan, 32% of people in Mexico are Garth Brooks fans, so that's going to be 0.32. We also know that the probability of you being a Garth Brooks fan and disliking the government is 8%, 0.08. We are asking, if we're at a Garth Brooks concert, we're only amongst Garth Brooks fans, so we're asking what is the probability of meeting someone who dislikes the government given that they're a Garth Brooks fan because they're at a Garth Brooks concert. That is going to be the probability of the intersection of D and F divided by the probability of F. So that is 0.08 divided by 0.32, which is a quarter. So in this scenario, a quarter of the audience are probably going to be people who dislike the government. Okay, think back a couple of videos ago when we did sequences of events. We used this piece of reasoning. We said that the probability of A and then B happening is equal to the probability of A multiplied by B after A has already happened. Does that sound similar? Sounds quite similar to what we are doing now. The probability of A and then B happening is the probability of them both happening. It's the intersection. The probability of B after A has happened, well, we know A has already happened, so what is the probability of B? That is the conditional probability, the probability of B given A has already happened. And now this equation here, if we rearrange it a bit, is our definition of conditional probability that we have been using. So we've already been using this. I just wrote it in a different way. But we've already been using this definition of conditional probability. It is how we construct probability trees and sequences of events. So as an example, here is a probability tree. Event A can happen or event B can happen first. And then after event A or B, event C or D can happen. And this is exactly what we've been doing before. So we start off along the branches. The probability of A leads to the event A. Probability of B leads to the event B. And then once A has happened, we're asking, how do we get to C? Well, it's the probability of C given that A has already happened. How do we get to D? Well, it's the probability of D given that A has already happened. And what's the end points of those branches? Well, once A has happened and C has happened, then both A and C has happened. So it's the intersection of A and C. And remember, how did we work out the probability of that event? That was multiplying along the branches. Multiplying along the branches in this case gives us the correct probability based on the formula we just saw. Conditional probability is also very related to the concept of independence. So I introduced this video by saying independent events, knowing one has occurred doesn't change the probability of the other, and a conditional probability is the probability of one happening if we know the other has occurred. Looking at the equation for conditional probability, now imagine A and B are independent events. If they're independent events, what do we know about them? Well, we know to get the probability of the intersection, we can just multiply the probabilities of the individual events. So the top of this fraction becomes the probability of A multiplied by the probability of B. And now we have a factor of the probability of B on the top and probability of B on the bottom that we can cancel out. So that gives us just the probability of A. And that is how I introduced independence. The probability of A, given that B has happened, doesn't depend on B happening. The probability of A given B is equal to the probability of A. And we can use this as another check for independence. If we know the conditional probability, we can use this as another check of independence. Finally, I want to talk about another real life case, the O.J. Simpson murder case, which is a famous case. And I want to talk this because this is an example of where people can get very confused with conditional probabilities. So, a bit of background. So in 1994, O.J. Simpson's wife was murdered. And he was known to abuse his wife. He'd been in trouble before for being a wife abuser. His lawyer at the time, at the murder trial, Alan Dershowitz, argued that this fact that he abused his wife was completely irrelevant to the trial. Why? Because he said only 1 in 1,000 abusive husbands eventually murder their wives. And that was so small it doesn't impact the trial. So he was saying the probability of being a murderer, given that you're abusive, is 0.001. And that may be true. He may be caught in real statistics there. But that doesn't make it irrelevant to the trial because he's asking the wrong question. What he should be asking is, what are the givens? Yes, it's given that he's abusive, but there's more givens than that. We should be asking, what is the probability that the abuser is the murderer, given that a murder has happened and the husband was abusive? What Alan Dershowitz failed to account for in his equation was that a murder had happened. So this goes to show that even some very intelligent people can get confused with conditional probabilities. And again, you saw this before. This is another example of what we call the prosecutor's fallacy, that we are not taking the correct things into consideration.